great pleasure to be hosting Aravindan. So Aravindan is a principal engineer in Google Research India, and he's also an associate researcher at RBCD Sci. I'm happy to add that. And before he came back and joined Google, he was a research scientist at Facebook, as well as a principal research engineer at Yahoo Labs. And Aravindan received his MS and PhD from the University of Minnesota's Twin Cities. His research interests include large-scale machine learning and natural language processing. And Aravindan is now a good collaborator, and I'm always amazed by the way he can connect, theoretical advances in machine learning to very, very practical applications, right? And issues that impact Google's products, performances, and things like that. Like amazing. Whenever I have discussions with him, I'm always thrilled. I'm assuming he's also going to enthrall us again today with his talk.
Thank you, Ravi. Thanks for the generous comment. We'll get started. Oh, I'm not. Can you hear me all right? Okay. Please stop me if you have any questions. This is going to be mostly an interactive talk. Let's see. I'll just get used to the clicker here first. Okay. Works. Oh, how do I go back? Okay. Great. So yeah, my name is Aravind. Nice to meet you all. Thanks for coming. So the work I'm going to present today is joint work with a whole bunch of people. I'm not going to read out the names, but with folks from IIT Bombay, IIT Madras, and also from Singapore here. I'll talk about the setup and the problem area. So we know of the internet today, right? And then the next wave of users that are going to come are not going to be like the people actually like us, right? These are going to come from India, different parts of India, Latin America, Southeast America, Southeast Asia, and so on. And it's expected we'll have around close to maybe 400 million new users. This is, if I move around, you can't hear me properly, is it okay? Okay. So we have a huge opportunity here because the kind of Okay, this is good. Are we back on? Start, okay. Yeah. Okay. So yeah. So this is a very good opportunity because the kind of problems that we're going to see today are going to be very different from what we've seen in the past, like what I was just saying. And Google search is a very powerful tool, right? And we have seen how Google search has actually impacted so many millions of people's lives. We want to see how we can do it for the next generation of users now. So what are the challenges here, right? These people who are now coming online have very significant different requirements than what the internet was traditionally designed for. Mostly mobile first, like most of us, I presume, don't have desktops anymore, or at least I'm not talking about the crowd here, but in general, people they access the internet, but they don't need a desktop, right? They're very app heavy. They don't use browsers as much. There's multimodal interaction. They just don't use text. They use video, audio. They use the mic to search on Google, etc., etc. And local language first versus English first. They just don't use English, right? And in the India market is a microcosm of all of the above challenges. And today we're going to talk about the language piece, right? And there are other pieces that we won't discuss today, but the language piece. So I'll talk about some recent launches that we've done in Google search. Some of my teams have worked on this, and we've made Google search better in some aspects. One is query translation. Like when you search for the query after series, like people who are searching who want to see it in Hindi earlier could not actually, we were doing literal translations. Now our query translation has become significantly better, and because of this we have seen much more improved usage of Google search for Hindi users, and users come back and use Google search more often than before, and so on. Basically the underlying reason being query translation. And query translation is an interesting problem because it is basically low resource. You don't have a lot of training data for this. How do you make translation systems work when you don't have a lot of training data as the underlying problem? Next thing is phonetic awareness. This is a very fascinating problem. I'll talk about the problem in more detail later. But the point is that when let's say Tamil speaking users say an English word, they're not trained in English, right? So what we observe is that they make certain types of spelling mistake that a Bengali user will not make, right? So there is a very clear interaction between your local language and English. And internet being predominantly English, people are forced to use English, right? So when you're forced to use English, you make some spelling mistakes, and those spelling mistakes are very, very dependent on your native tongue, right? And that's an observation. And how do you fix it? And it's very phonetically inspired. How do you fix such kind of problems is another thing that we have done. I'll talk about that. And code mixing is another interesting thing where you just don't use Tanglish, English and so on. People just don't use one language; they use a combination of languages. And how do we make multiple Google products work when you have code mixing is the next question. So we'll talk about these 2-3 problems today, right? Low resource machine translation, phonetic awareness, and code mix language understanding. We'll go one by one, and again, please stop me if you have any questions. So this is of a paper that we published in EMNLP 2 years back, and you can go look at the paper for a lot more details there. But I'll kind of walk you through the main challenges and the kind of the key ideas in the paper, right? So neural machine translation is like how many of you are familiar with some of these things like neural machine translation or in general machine translation? Okay, roughly 30% of the people, but most of these things may not require a lot of details, but again, I'm happy to go into some more detail, and if you have any questions, please feel free to ask. So, but one high level thing that you can assume is that like any other neural system, neural machine translation will require a lot of data, right? It's super data hungry, but it's very, very effective. So, because of that reason, it is subpar under low resource environment. So, be it query translation or be it, let's say I want a good translation model for, let's say, Tulu to English, right? So you won't have a lot of training data for it, and how do you really make it work? That's a problem. So there's a lot of data augmentation strategies that have been tried, right? There's a technique called back translation, which I'll talk about next. So let's say that you want to train this Gujarati to English model, right? So there's a decent corpus which is about 162,000 parallel data points, right? And that's actually pretty small, right? For if you want to really train a good model. So what we do is there's a technique called back translation, but there's very, very large corpus of English data available. Like you want to go from Gujarati to English. So you train an English to Gujarati model, right? You kind of flip the order. You actually want to train a Gujarati to English model, but you actually train the other way around. You train English to Gujarati model using the 162K, and then you apply this on the English. You have this very large corpus, millions of data points of English data, right? You apply it on that, and that will give you corresponding Gujarati data, right? Because you have trained the English to Gujarati model. Now you have English Gujarati parallel sentences, and now you can flip the order again. And then you can kind of augment your 162K data points with this back translated data, as it's called, and then train a model. This is a very, very popular technique, and it's very effective. I mean, I'll show some numbers, and this is super effective technique, right? But there are some issues with this technique. There are two main challenges with low resource and empty. One is the quality of data is very, very poor. 162K is actually reasonable size, right? But you can assume that when you actually have a lot of, when you talk about low resource data, there is very low quantity and very low quality also, right? So when your back translation model, in the example that I gave, the English to Gujarati model, if it's not a very good model, then your back translation data it's not going to be very good, right? So the quality of the data is poor. The other thing is that it's often cross-script, right? By cross-script, I mean Gujarati is in the script, like say Devanagari script, and then your English is in Latin script. So there's some very good studies that have shown that when there is script overlap, that also helps the translation model, and that is gone here, right? When you have cross-script, that's gone. So basically, and the number of cross-script tasks in this called WMT benchmark is increasing over the years, right? 28% in 2017, and in 2020 it's about 63% of the tasks, right? So the amount of cross-script is increasing, and these two are the most important challenges in low resource and empty. So as I said, back translation data is basically, it's varying quality. So how do you fix this? So one is either you can use all the BT data, and the problem with that is that you are now mixing good quality and bad quality data. The other very common alternative is just throw away just filter out the BT data, but the problem with that is you're throwing away data, and already it's very data resource poor, so you should not do that. So the idea that we had is it's a very simple idea. What I'm going to talk about, there are two ideas that I'm going to talk about, and both of them are very simple but surprisingly very effective. So we just give the hint to the model saying that we just try to predict the quality of the model, quality of the pair, and then we try to give a hint to the encoder about what is the quality of this data pair, right? I mean, so we say that this is an extremely good quality data point, pay more attention to it, or you can say that it's a very low quality data point, try to learn from it whatever you can, right? Something like that. So that's the idea, and the next one is called translate tagging. Basically, what we do is, the first one was an encoder thing. Sorry. It was an encoder hint. The next one is a decoder hint. The decoder hint basically is that so your decoder is now kind of decoding, like you're giving a input, let's say Gujarati sentence, you want to go to English. So you can do, there are two types of things, two types of target sentences, right? Either you can, every word can be translated, or there could be some words that could be transliterated, which is basically the cross-script problem, right? So we actually say, if the target is actually pure English, right, then we say it is actually translation, TXN, there is a second tag, right? Or if there's a mix of translation and transliteration, we say it's both. Basically, we are asking the decoder to predict whether a transliteration task is involved or a pure translation task is involved, right? So it's a very simple thing, and the decoder can actually become pretty effective as doing this task, right? So as I told, there are two hints that we are asking to do. One hint is on the source side, which is what is the quality of this pair, and one hint is on the target side, which is is a transliteration required or not. Just these two things, which is very easy to compute. And so here's an example, right? So the first one is quality tagging. Bin 4 is actually high quality bin. It says that, okay, this is a very good quality pair, right? Bin 1 is low quality. You just say on the source side, we say bin 4 or bin 1, like high quality or low quality. And for translate tagging, we say the first example, every word on the source is it's translated on the target, right? On the other hand, the second example, the number and plate are transliterated, right? So we give a target called both, right? There's a prediction is called both, and we apply. We can apply them in combination. So you can have bin 4 and both also. In the final example, right? So this is basically the idea. That's all, right? It's a very simple concept, and we have seen many people refer our paper, and they've been able to reproduce this idea in multiple contexts, and it seems to work well. And is it clear, like the idea? So we did it on like 3 low resource languages with whatever I've shown here, the amount of training data. But the important thing to notice here is that we have a lot of monolingual English, 23 million points in English, but that's monolingual. It's not parallel, right? And then we measure encoder decoder models and so on. So I'll talk about 2 baselines here, but the paper has got a lot more baselines and a lot more comparisons. I just want to give you a flavor of what we do and how well this is performing. But you can look at the paper for more details, for more baselines and more comparisons. So the first one is saying that if I just use only the bytext, which is the parallel data, how much of blue do I get? Blue is basically a measure of I translate Gujarati to English. I have a reference English sentence. Comparing the reference to my generated machine generated model, what is the similarity between these two? You can think of it as to be some similarity metric, right? So higher the better. So only with bytext you get whatever those numbers are, and you can see just by doing this BT, which is basically the back translation technique that I talked about, you can significantly improve the performance, right? That you can already see, right? The question is, can you do better than this, right? And the answer is yes, which is by just doing quality tags. Now you have to just compare the full BT versus what you can do with BT with quality tags, let's say, right? And you're able to see that across all the 3 pairs, we're able to improve over on top of BT. Similarly, if you compare with translate tag, again, you're improving further. Not further yet, but you can just still compare each of these pairs, and we're doing better. And finally, when you do both, actually these numbers that I'm reporting, this is probably 2 years back. I don't know the latest numbers now. At that time, this was the state-of-the-art numbers for all of the pairs, right? So it was SOTA for all of these language pairs. This was the state-of-the-art numbers that we could get. We were able to beat even multilingual models. Hindi to English model 31.6 was at that time higher than the multilingual model's performance, right? So it's a pretty impressive performance, and with it's a very simple technique, and it works really well. The takeaway was, if you have a lot of data, instead of throwing it away, if you're able to mark it with quality hints, these sequence to sequence models can actually use them. So it's not just a machine learning or machine translation thing. Wherever you use sequence to sequence models, I think this kind of general idea should work, right? Similarly, if you're able to predict an operation, an intermediate operation, that's the kind of the abstraction of what we have done here. That can also help the decoder do better. So these are the kind of takeaways from what we did from this. Phonetic awareness, and Ananya is here. This is joint work with Ananya. So one of the things that I talked about this example before, right? So where people want to say a certain word in English, but then they are kind of influenced by what native tongue they have. So the entire web is about 55% English, right? But then the amount of people who speak English is actually pretty low. So because of that, what happens is they have to navigate the web in a language that they don't know, right? And they are forced to do that. And while doing so, they make mistakes, like be it like typing the queries or like utterances in ASR or whatever. But then, how do we make systems more robust to such users, right? Because these kind of users are going to become more and more common, right? Like the phone is in everybody's hands today, so we can't expect them to learn English, right? And high quality content is going to take a while to be on the internet. So there's very, very good content on the internet available. So how do we make these users actually use this content is an important challenge, right? So these are all some examples that we got from real world. In fact, the one on the right that you see is from one of my friends' parking lot in Bangalore. And I'm sure that you've seen such examples a lot, right? They know the word of vegetable, but they don't know how to write it. They will write it as the way they would pronounce it, right? Like for example, no parking June. There's a confusion of how, I've seen it a lot in Tamil Nadu also, right? Like in Tamil it doesn't have a differentiation between ba and pa, right? So when there's an English word that has got this ba and pa, they tend to kind of confuse between the two. There's no difference between fa also. There's no fa in Tamil, right? So all of these things there's no difference between tha, dha and tha, right? So all of these things get confused because when they pronounce English words, and we have observed it in query logs, people have this problem when they type queries in Google search when they type such words, they will make such kind of mistakes, right? And these mistakes will depend on what is your native tongue. If you're a Bengali speaking user, your mistakes will be slightly different. If you're a Gujarati speaking user, your mistakes will be different. So the idea is, can we actually recover those mistakes, right? And the answer is yes, and we were able to make search better because of some of the things that we've done here. So the point is, sound is not present in the native language, and there's lexical overloading, right? So let's consider the word brave. A native Bengali speaker, you might know that Bengalis have this confusion between v and bh, right? Like for example, my friends call me Aurobind, right? There's no v. V is not very pronounced for them, right? So there's a va bh confusion. Similarly, in Tamil, there's no ba and pa, so there's a ba pa confusion, right? So there's likely to misspell as brave, and here as brave, for example, right? These are possible misspellings that can happen. I'm just picking some examples here. I don't know, it's not real queries, but some examples to show you what I mean. Right? So the goal is, can we build inclusive systems that can understand from diverse users and that are robust to such kind of L1 inspired. L1 is basically your native tongue. L2 is English, right? Can we build systems that are robust to phonetic misspelling, right? In our study, L1 is Hindi, Bengali, and Tamil, and L2 is English. So we have three things that we did here. One is we have a model that can actually do this, and one thing that you can do, right? You can go and collect training data. You can go interview a whole bunch of users in Tamil, Bengali, and whatever, and then you can collect training data. But this is of course not scalable, right? Like and there are so many dialects, and if you go to Coimbatore, there could be different types of mistakes. If you go to Salem, it could be different, and it's very hard to collect training data basically, right? It's especially for a country like India. And think about what happens. Same thing with Spanish, same thing with French. So right, it's very hard to collect training data if you want to do it manually. Our goal was to do it totally unsupervised, right? Can you do it without any supervision, right? And that's what I'll talk about. Second thing is, we also released a benchmark. There's a benchmark called Superglue. I don't know if people have used it. We released a benchmark on top of Superglue called FunGlue, which is basically phonetically inspired glue or something like that. And we showed that today's state-of-the-art techniques can fail significantly if you start introducing phonetic noise, right? And then third is, we showed with a very simple pre-training technique, we are able to actually recover a lot of that, even without knowing what kind of spelling mistakes or the phonetic patterns of mistakes that there are. Okay, so the um, the kind of the magic here is basically transliteration. So transliteration is a technique by which, let's say you write a word in Tamil in the Tamil script, you can write the same thing in English without translation. You just when I say, I don't know, um, let's say Magi, right? I can say Majai, and that is it isn't translated. It's just whatever I said in Tamil, I'll just write it in English, right? So and we use. I'll talk about how. I'll give an example of how we do it. We use that first. We use a transliteration model, and we do what is called, we introduce a technique called round trip transliteration to actually mine such things. And then after we do that, then we can combine that with a phoneme grapheme model. I mean, I won't go into the details here, but the rough idea is that sorry about that. But the rough idea is that once you know the distribution of confusions between a particular phoneme, you can take a word and split that word into its corresponding phonemes, and then you can start flipping phonemes, right? If I will have a word, if I have a phoneme, and then that phoneme I'll flip it to something else based on what I've mined in the previous step. Once I flip it, and then I'll find out, I'll take it back to the grapheme. You can think of grapheme to be the way you write things, and phoneme is the way you hear things. First you go from grapheme to phoneme, and in the phoneme space you will do this flipping, and after you flipped it, you'll go to the grapheme space again, which is the way you write it. If you do this, then you will start introducing these phonetic noise, right? That's the idea. That's the second step. I won't talk about that in detail. The paper has some more details in it, but that's the kind of the rough intuition of how we do it in a probabilistic sense. So here is how we do it, right? We take an English word, Amazon, let's say, and then we actually transliterate that word into L1, which is basically your native language, Hindi, right? So, and we do top 5 transliterations. The idea, I mean, the kind of the takeaway point is that when you do this, it's a lossy process, right? Because not everything in English can be said equally in the same way in Hindi, and that's exactly what we want to capture. When we do that, already some information in Amazon is lost. The Z to J has already happened here, right? So you see Amazon. I don't know if everybody can read Hindi here, but the first one says Amazon, right? So the Z to J has already happened, because there's no Z. I mean, it cannot be pronounced perfectly well in Hindi, right? And then when you take that and you go back to English, it tries to do the same thing, and that's how you get this Amazon. So you have a J there, right? And now you have this. Now you have an Amazon. You can take on the right hand side, I've shown the phonetics of the same word, and then I've given on the bottom, I also have inside the box there is phonetics, right? Now you can do this on like millions of pairs or millions of words, and then you can start to align them, right? If you start to align them, you'll see that there's a Z to J confusion here, right? So like that, I mean, you can basically do it for every type of transliteration model, and you'll start getting these pairs of phonemes, right? Which basically can get confused. But the nice thing about this technique is that the more and more better your transliteration techniques are, you can start to get more realistic variations or realistic issues or realistic kind of problems that you'll see. And there's no human labor that's involved here at all, right? So we did this thing called, we just did this thing for plausibility, right? I mean, let's say that biphone, we call this model biphone, by the way. Plausibility is a question that we asked to raters, how, like, we took native speakers of Tamil and all that, and then we said, okay, can you tell me how likely is this spelling mistake? Will you make this spelling mistake, right? And so basically, if it's evicted, will you actually make this evicted or not, right? And making sure that we're on time. Okay. So I'm just talking about 3 phoneme shifts here, like va, W to V, which is va to va, and then G to G to K, and va to ba for Bengali, right? So I took these examples because these are very, very specific to each of these languages. And word W to V is, you can see those examples, wheat to wheat, right? I mean, like you can see those examples, right? So these are all very, you can see that they're actually possible, no? And so we had reasonable agreement for Bengali and slightly reasonable for not as high for Tamil, but at least if you look at, when you look at the examples, they definitely look more probable. And for Tamil, you can see, right, G, K confusion is there, and exam to exam, you can kind of think about why these things can happen, right? So how common are these misspellings on the web? You don't want to do something that's very, very uncommon. You don't want these models to generate some spelling mistakes that are not even present, right? So we took the common corpus, which is actually pretty big, right? And then we looked at coverage. For example, this graph shows, forget the exact, I mean, as you go on the right, you are becoming less precise, you can think of, right? Like precision drops, right? I mean, I'll talk about how we drop precision. As you drop precision, coverage can improve, right? So we see that with about like 80% precision, we have about 0.5% coverage on the common crawl corpus, and this corpus is actually pretty big, right? It's still a very English dominant corpus, and even with this, it's like, I mean, tens of millions of sentences that have this problem, right? So that says that this is not like a very tail issue, it's already there. I mean, and this is I mean, unless otherwise we did this, we wouldn't have noticed that there is even this amount of noise in the current common crawl corpus. The point is that the such kind of content is just going to get increased. I mean, it's going to become more and more as people produce more such content. We're going to have this problem more, right? So we found that it's not a trivial amount of data that's already present in the web. We already have it. Right? That's the kind of the takeaway. So I'll talk about this benchmark, natural language understanding benchmark, and so basically we took superglue, and then we have superglue has got the 7 tasks that we worked on, and then we actually took a bunch of them and used our technique to actually go corrupt it, right? So we didn't corrupt a lot of tokens. As you can see, roughly 30% of the tokens we corrupted only on the validation set, by the way. And then the examples, and then we look at number of examples with noise in it, and that's actually a substantial number. And this is an example of what that is, right? So so the possible becomes like what's shown here. Similarly, laughter becomes what's shown here, and so on. So these are some examples of what we did, right? So we made sure that since this is all on just validation data, I showed a previous editorial like a human labeling task, right? Humans went and looked at each of these things and made sure, I mean, had multiple people, maybe 5 people, I don't remember, but we had multiple humans checking the validation set, and we have verified that those were real or like plausible corruptions, right, or plausible spelling mistakes. So now what we have is we have superglue, but now the validation set of superglue is corrupted with biphone, and that is also passed through a human being, and we have a very cleanly corrupted version of superglue now, right? And that's what we call fun glue. And what we see is this is for one particular task in superglue called reading comprehension with common sense reasoning. So the superglue MT5 is a very common, pretty powerful sequence model, and then there is byte T5. Basically, the difference between them is the encoding is different. So the byte T5 is basically byte encoding versus tokenization in the MT5, which is learned. So what we see is that like close to like 71% performance on this particular record kind of drops to close to like less than 60%, right? Like more than a 10-point drop. But it's not as bad for byte T5, and that's interesting. But the other most important thing to notice is that I mean, it's not shown here, but the paper has a table. We see that this drop is consistent across all the tasks, right? I mean, pretty much for all the tasks, when you introduce this kind of confusion, this kind of when you start evaluating on this on the fun glue benchmark, there's a significant drop, right, on both MT5 and byte T5, right? And byte T5 has got it's slightly more resistant to phonetic noise. So sorry. So so the fun glue benchmark is now public, and people have started to use it, and we've heard some feedback about it. But the most important thing that we kind of wrote in the paper was you don't need to know exactly. So as you remember, right? Like the way fun glue did this thing was I talked about biphone and how we actually corrupted it, right? We did a very, very simple technique, right? We had a pre-training technique where like you have the span prediction task, right? Where you have you mask out SOFA design and you're predicting SOFA design. This is the very standard thing. In addition to that task, we also did one more task, which is given the word building, can you actually predict the phoneme sequence of building, right? So when you do when you add this additional task of let's say 20% of your task it's a task mixture. When you start doing this, does your model get better? Like, I think the most important thing to notice here is that the phoneme prediction task has got nothing to do with the kind of mistakes, right? You're just asking the model to predict the phonemes, and that's all, right? We're not talking about L1, L2, we're not doing any of that stuff, right? We're just saying just predict the phonemes, right? and we found that this alone can really help. So and it can help I mean it can help by T5 but not MT5, and that's also another thing. So if the same super glue on left hand side you have phonetic MT5, which is basically MT5 trained with this additional objective, which is the phoneme prediction objective, and then on the right hand side you have byte T5 again with this additional objective of phoneme prediction. We're able to see that on the, I mean, byte T5 is able to actually recover some of the performance, right, that it lost by using this phonetic pre-training, and we were very surprised to look at this because byte T5 does not have, this training does not know anything about L1, L2 mistakes and all that, but still it recovers it. But the reason why I think phonetic MT5 is actually losing out, I mean, this again something that we haven't dug a lot into, but we have a very strong hunch as to what is happening. So basically, phonetic MT5 does its own type of tokenization, and the additional task doesn't help tokenization become better or make add additional robustness because the tokenization is actually almost independent of the phonetics now, right? Because of that, it is very hard to transfer that to the spans or the tokens that the model creates, and because of that, it doesn't really help, right? So, but that's the current hypothesis, but we haven't studied in more detail. But it would be interesting to know what causes this problem. But consistently, we've seen that byte level encoding techniques seem to definitely perform better, correspond to compared to tokenization methods. So last thing would be the the code mix language understanding. Any questions so far? Okay. So this is a paper. The last paper was an ACL of last year, 2023, I think. ACL this year, and this is an EMNLP of the year before. So, how do we make models understand code mixing better? Right. That's the topic of this. I mean, I think I told you the three things just to kind of remind you. The first one was to make translation models better. The second was to make, I mean, and people use translation a lot. I mean, to search the web, right? So that's why that's important. Second one was this phonetic robustness, where people are forced to use the web while they have a different native tongue. And third one is the same, right? So think of this to be a translation model, but the techniques are kind of broadly applicable. So, I mean, I don't know if, I mean, you're probably not in this generation of seeing this ad, but it's a pretty common ad that used to air before, but it was a very good example of code mixing. But the point that we're trying to make, or what we try to do in this paper, is can we actually do this monolingual sentence to a code switched sentence, while controlling for multiple attributes of the code switched sentence. I'll tell you why that's important. So I think you know what code switching is, but here is an example in Spanglish and in English. So I'll go with the English one. Kal Bangalore ka weather kaisa rahega. So how is the weather in Bangalore tomorrow? So the ones in blue are Hindi and the ones in red are in English, right? So you tend to mix Hindi and English, right? So it's very diverse. Code switching is very diverse. There's no one right code switching sentence, right? The reason for that is because first generation people don't tend to use a lot of English words. Let's say, for example, if you talk about people in the IIT Madras campus, if you talk to somebody in Tamil, there's a much higher chance of using English words, right? As compared to if you go to a slightly more remote place in Tamil Nadu, the chance of using English words is much smaller. So the amount of English words can change, and both of them are code switching, right? So code switching is not one thing. It's like, there's a very wide variety of code switching. There's a diversity here. Second thing is, depending on where you get the data from, news also has code switching, and reality TV also has code switching, right? But news tends to be formal, while reality TV tends to be very informal, right? So you can talk to your parents in code switch Tamil or Hindi, and you can talk to your friend in code switch Hindi and Tamil, right? I mean, and both of them are code switched, but the way you're going to talk is very different, right? It's because of the formality. So these are all examples, and this paper actually studies it really well. It came in ACL 2021. Like, what is the reason for code switching, and what is the reason for this diversity, right? And why is this important? It's actually important for, let's say that in Google Assistant you set this thing, set an alarm for tomorrow, and you can do that in so many different ways, right? You can you can use a matrix. Matrix language is the language that you use, and you actually embed different other languages into it. In the first example, your matrix language is Hindi, right? I mean, you use a Hindi sentence into which you've put English words, or your matrix language can be English, right? Or you can be very formal. You can say kar dijiye. You can be very formal about it, and all of these things should have the same outcome of create alarm, of date time. It should kind of parse out the same way, right? I mean, so people can say the same thing in so many different ways, and diversity again is a problem here. So similarly, you can augment your training data with diverse examples. Similarly, generation of diversity is also important, right? So let's say that if the user says something, you want to respond to the user in the same way. Let's say the user is talking to you in a very formal way, you want to be formal about it. Or if you're talking to somebody, if the user is using a lot of Hindi words, you want to talk back in a lot of Hindi words. You don't want to talk back with a lot of English words, right? You want to kind of match what the user's code switching was with what you are generating, right? So for generation also, like code switching control is very important, right? So the point I'm trying to make is that being able to control for diversity, having a control for diversity is very important. We have all these models today, but in real production systems, the most important thing is to be able to control, right? I mean, you can't just assume that the model will do the right thing. You have to be able to put the right kind of levers to the model so that you can actually control for important things. Right? So we have this model called COCO, and there are like primarily like three contributions of what we are doing. One is, when we have this encoder decoder model, right? But now we can actually, it's a sequence to sequence model, and can we actually do controls? We introduce two types of controls, encoder side controls and decoder side controls. I'll talk about what they are. And we have three kind of contributions in this paper. The first one is, can we control the attributes responsible for diversity? Like, I'll define what diversity means in the context of code switching, and then I'll talk about how to actually control for them. And then we have both techniques. We have encoder side techniques and decoder side techniques. When should you use encoder and when should you use decoder, and what is the trade-off, right? And we'll talk about that. And also we open sourced a large data set of code switch data. I mean, like people can start using that. So, I mean, there are basically three types of attributes that is very popularly studied in the linguistic literature, right? People have studied this a lot. So, first one is called code mixing index, right? It's basically the number of words, it's the ratio of number of words in one language versus the other, right? So, in the first example, you use a lot of English words. Second one uses a lot less English words. Basically, the fraction. That's all. So, the second one is called switch point index. Switch point index is basically how frequently you switch between two languages, right? Let's say that you had a code mixing index of 50%. Let's say 50% is basically half of the word will be in Hindi and half of the words in the sentence will be in English, right? You can do the half by alternating between two languages, right? The first word English, second word Hindi, second, third word Hindi, English, and you can just keep on alternating. That's one way of doing it. But people don't do that. People talk a few words in Hindi, then switch to English, then talk a few words in Hindi. There's burstiness in the way people talk, and that's what switch point index controls for. It's basically burstiness of one language versus the other. And the third one is formality, right? Like how formal you are. Like so the same thing you can say in a formal way versus an informal way. So what I'm going to talk about now is, can you build a translation model or like a sequence to sequence model, and on the source you give a Hindi sentence and say that now generate a code switch English sentence with 20% CMI, 40% SPI and informal, or 40% CMI, and you can basically, can you control for what you want, right? Just instead of saying that I just want to go from this to this, can you actually control for what is that, what percentage or what is the value of CMI, SPI and formality you want on the target, right? And that is very important for the reasons I told before, right? And the answer is yes. That's what we did, and we are able to actually control for all of these things pretty precisely. So the question is like, what do you mean by, first of all, what do you mean by encoder control and decoder control, and when should you use both, right? And that's what we'll talk about first. So encoder side control is usually very, very helpful and very useful when the ground truth is available and when the full range of values is available. I'll tell you what I mean by that. Let's take example of CMI, right? CMI is very easy to understand, no? So given a pair of sentences, I can easily calculate CMI, right? So that ground truth is available to you, right? And usually CMI between 0 to 1, most likely the full range of values is available to you, right? So if that data if that information is available to you at the time of training, using encoder side intervention or encoder side control is actually very effective, right? Um, yeah. So because of that, we use encoder side intervention for both CMI and SPI, because both of them you can calculate for the entire training data, right? On the other hand, let's say formality, right? Formality is not available to you as an example of what is not available to you during training time, right? So your training data is basically, here is a Hindi sentence and here is a code switched English sentence. It doesn't say whether the translation whether the target is actually formal or informal. It doesn't say any of those things, right? You're just given this thing. You don't know during training. Um, you don't have for every training instance the value of the um, attribute that you want to control, right? When you have when you have a situation like that, for those decoder side controllers is actually much better, and that's what we showed here. And the other thing is that formality is also domain dependent. I mean, what is formal in one domain could may be different. This is an example. Formality is an example, but the point I'm trying to make is that if the information is not available during training, decoder is a very good place to actually intervene, right? So the encoder side control is actually a pretty nice idea. It's also in this paper from before. It's a fun idea. Basically, like, you take the output of the encoder, the representation that the encoder emits, and to that you add a trainable vector, right? That vector is V, and then that vector also you're learning, right? Along with the backprop, you learn the vector also. Those are parameters of the model. And then let's say that I will basically multiply, like, I know the target, right? So I mean, let's talk about one particular training example. For that training example, I know my target. I can calculate what is the CMI of the target, and let's say that's 0.25, right? I'll take the vector at that point of time. I'll multiply with 0.25, and that vector I'll add to the current hidden representation that the encoder emits, and that combined representation is what the decoder will try to decode, right? Basically, somehow there's a embedding that we're trying to learn, which somehow encodes what it means to be code switched, or what it means to be CMI, right? I mean, the semantics of CMI gets encoded into the vector V, and the amount you actually multiply the vector by, the scalar that you multiply, is the amount of CMI that you want, right? And you can train the model this way. If you train the model this way, you're able to actually control for CMI, right? So what we actually found out in this paper was that it's possible to have multiple vectors, right? This paper just did one vector. We were able to actually add multiple vectors. You can have one vector for CMI, one vector for SPI, right? I mean, it's possible to do multiple vectors and works pretty well. And it can also kind of very cleanly interpolate between two. So CMI, let's say your training data only had like 0 to, let's say, all the way up to, let's say, 0.7, or let's say 0.6. Between 0.6 and 0.8, let's say you didn't have any CMI training data, but then you had data again from 0.8 to 1. But this model can cleanly interpolate even in between. Even though it didn't see it, it's still able to interpolate in between, right? So that actually was pretty cool when we actually found that. And decoder side control is also very nice. So the idea is that, like I told you, there is no training data now, but you can build a classifier. Let's say you can say, here is a classifier that says whether a particular sentence is formal or informal. What you do is basically, when you generate your beam candidates, right, you reweigh your beam. So basically, I don't know, beam is basically, you do this auto-regressive decoding, like you've decoded your word until, let's say, the kth point, predicting the k plus 1th token, and when you predict the k plus 1th token, you have a set of candidates with you, right? And those candidates, you have the score that's being produced by the language model. To that score, you also have a kind of a linear combination of that score with the score of the classifier. If I pick this token, will the output of this be formal or not, right? Let's say you want to kind of push this to be more formal, you actually start weighing it with more formal words, right? So the idea is to actually start picking words and tokens as guided by this probability, by this classification model, right? So you just train your model as is, but then during beam decoding is when you intervene. So your underlying model is frozen, you don't touch the model, but during inference time is when you start intervening and you start actually picking different beam candidates. If I gave the weightage of the classifier to be 0, you will just produce as is, what you produced before. The more and more you give weightage to this thing, you will start actually deviating from the language model, but you will be more formal, right? So the goal is to actually find a good balance between both, right? Social metrics here. So so basically the task is to go from Hindi source to code mix target, right? So the question that we're asking is, if I know the target CMI and SPI, can we do better, right? So we are looking at three metrics. One is blue, and then the correlation of CMI and the correlation of SPI. By correlation, I mean the model has produced a bunch of output, and what is the CMI of that output versus the reference? So what is the Pearson's correlation of that? Similarly, the model has produced output, and what is the SPI correlation between the model's output and the reference, right? So what we see is, first of all, when you control for both CMI and SPI, we're able to actually increase the blue, because we're able to use this additional information that that this is what I need to. So let's say that I'm going from source a Hindi sentence to a target in a code mix sentence. If I know what is the target's code mix index, I'm able to produce something that's more closer to that, right? And we're able to use that information more effectively, right? Which is what the first set of bars show, right? And the more information you have, the green one, which is basically CMI plus SPI, does much better than the red and the yellow, because there's more information. We're using both the CMI information and the SPI information. The second one is basically what is the CMI correlation of the output compared to the reference when I'm controlling for that particular thing. So when I control for correlation for CMI, which is basically the red bar, I get very high. I get very high correlation between the reference CMI and the model's output CMI, right? So that's because I'm basically controlling for it. So red and green are roughly the same because they both are being controlled for CMI. Yellow is not good because I'm not controlling for CMI in that, I'm controlling for SPI, right? And then similarly, when you go to the last thing, similarly red is poor for SPI, but yellow gets better. And green becomes really good for both CMI and SPI, because SPI and CMI are also kind of correlated with each other. But the point is that we're able to produce very high correlation between the reference and what the model outputs by being able to control for it. And this is an example of decoder side control, where we are asking the model to become more and more formal, right? Like we are asking the model to, I talked about the classification model, we are asking the model to produce more formal text. So the data are shown two model outputs, with and without control, and test arms to make the output more formal. And we see that overall we are able to make it more formal, or equally or more formal is more than 75-80%, and less formal is about 22%, right? The reason why it's less formal is still a big chunk is because you don't want to change the meaning of the sentence, right? Like you want to preserve the meaning, and that's the, and there are sometimes you can't actually do that as effectively, but you can also think of that to be like a good headroom to go understand that more and actually do better. But those are the examples that we found, like, it's very hard to change without changing the meaning of the sentence, making it less formal. And some human evals on how encoder and decoders actually perform, right? So you took the same the output of the model and the reference, and the pure encoder model and decoder model, see what happens, right? What we see is that encoders are usually very, very good at preserving meaning, right? And while decoder is not able, is able to achieve the target, but is not able to preserve the meaning, because primarily since you are actually changing the beam candidates, you can achieve the target, you can make it more formal, but while doing so, you may actually change the meaning of the sentence also, right? So there are some more things in the paper, but I'll probably not go through this in a lot of detail. The most important one is that we're able to take some of these the more important benchmarks, and we show that this thing helps. And I guess the most important thing that's useful here is we also released a data set called Diverse All CS, which is basically COCO generated code switch data, which people can use for training their models. I guess that's pretty much it. Any questions? Please go ahead. Yeah, so it's a very good question. I don't know if I have it here, but the phonetics, some of the there's a language, just like you have. We have our languages, right? There is a language released by CMU which actually captures the stress, right? Depending on how you place stress on different parts of the word, different phonemes get produced, right? Our model doesn't handle that. I don't know if I have it. I mean, the paper has it. So EH1 and EH2, as an example, these are two different phonemes. These are A and A, But the thing is that where you actually place the um, place the stress is different, right? And there is data available, right? If you go look at the CMU lexical something it's called, I forgot the name. The data is available, but our model doesn't do it. But it is possible to actually model that. Right? I mean, there is, and many of the ASR systems actually make use of the information also. Any other questions? Cool. I'm happy to talk later also, but thanks for the for attending this talk, and nice to meet you all.